Assalamu alaikum. This lecture is about NFA and DFA equivalence. First of all, we will see that both NFA and DFA are quintuple, that is combination of 5 objects where order matters. The first element is denoted as capital Q, which is the finite set of states. The second element is denoted as sigma, which is the finite set of alphabet. The third element is denoted as sigma, which is the transition function. Here the transition function is a little bit different for NFA and DFA. This transition function is not same for both. Fourth element is the initial state, denoted as Q0, and the fifth element of this quintuple is the set of accepting states or final states. Next, we will see the differences between NFA and DFA. As I told you earlier that the transition function of a NFA and DFA is not the same. First difference is that in NFA, epsilon or lambda or empty string transition is allowed, whereas in DFA, empty string transition is not allowed. The second difference is that for each input letter or for a single input letter, none or multiple transitions are allowed at any state of NFA. Whereas in case of DFA, minimum or maximum, only one transition is allowed for single input letter at any state. Keep in mind that epsilon is not part of the set of alphabet. Now we have to prove that NFA and DFA are equivalent in power. The first step of our proof is that every DFA is itself an NFA, which is easy. The second step is to prove that any NFA can be converted to an equivalent DFA. For this step 2, we have to do some work. As we have to convert NFA to an equivalent DFA, so we will see how we can accomplish that. Here we have been provided with an NFA, which is the quintuple set of states which are 1, 2, and 3, set of alphabet comprising of input letters A and B, and the transition table. Fourth is the initial state, that is the state 1, and the final state is also the state 1 in the NFA provided to us. Now we will see the steps required to convert this NFA to a DFA. The first step is to find the states of our DFA. Here we can see that our NFA provided to us has the set of states denoted as capital Q, and the equivalent DFA we are constructing, I have denoted the set of state as capital Q dash. The states of the DFA would be computed as 2 power the count of the states of NFA. As in our case, the NFA consists of 3 states, So the corresponding DFA we are constructing would contain the states 2 raised to power 3, that is 8 in number, which would be the power set of Q. Q means the set of states of NFA. If we take the power sets of Q, then the states we got are the empty set, state 1, state 2, state 3, then state 1, 2, state 1, 3, state 2, 3, and then state 1, 2, 3. The next step is to find the initial state of DFA we are constructing to prove the equivalence of NFA and DFA. I have highlighted the initial state of DFA as Q0 dash, and the initial state of NFA was given as Q0. Initial state of DFA would be the combination of initial state of NFA and any other state which is lambda reachable from the initial state of NFA. As in our case, the provided NFA has the initial state 1, and the lambda reachable state from initial state, which is state 3. So the combination of both of these states, that is state 1 and 3, would be the initial state of our DFA. If in the NFA there is no lambda transition from the initial state, then the initial state of NFA and DFA would be the same. But this is not the case here. The next step is to find the set of accepting states or the final states. The simple rule to keep in mind is that every state nesting the final state of NFA in it would be the final state in the DFA we are constructing. As we can see in the provided NFA, the final state is the state 1. So all the states of our DFA nesting the state 1 would be the final states of our DFA, which are state 1, state 1, 2, state 1, 3, and state 1, 2, 3. The next step is to find the transition table of the DFA. Since our DFA is now the combination of states in a single state, so there is a modification in the transition function. Instead of writing capital Q, I have written down the 2 raised to power Q, which indicates that now we have to see the behavior or the transitions for each input letter at the combination of the states to satisfy the transitions of our DFA. Now I have listed the 2 scenarios to satisfy the transitions. First scenario is in our DFA at state 1 we have to satisfy the transition for input letter A. For this purpose we have to consult the same transition in the NFA. As in the NFA there was no transition for input letter A at state 1. So in the corresponding DFA we are constructing, we will be pointing this transition to the phi state or the empty state. About how we will satisfy the transitions for the state which comprises the multiple states of the NFA. Here, for example, in our DFA we have a state 1, 3. Now we will see how we're gonna satisfy the transition for the input letter A at this state. For this purpose, we have to consult the same transitions on both of these states nesting in 1-3 separately in the NFA provided to us. The first state in state 1-3 is 1. We have to consult the behavior of state 1 on input letter A, which was not mentioned in the provided NFA, so we are pointing it towards the phi state. And now we have to take a union of this behavior with the behavior of state 3 at input letter A, which is the resultant transition towards state 1 and state 3. In the NFA provided at state 3 on the input letter A, there is a transition towards the state 1 as well as there is a transition towards state 3 itself, as the lambda is being concatenated with the input letter A. So we will consider the lambda transition after the input letter. Again, we can see that at state 3 on input letter A, there is a transition from state 3 towards state 1, and there is a transition from state 3 to state 3 itself, as A is being concatenated with lambda, and lambda doesn't appear on input letter, so we don't need any input to initiate the lambda transition. Now, by taking union of the phi state and the 1-3, the result is the state 1-3. Next, this is the complete transition table listed here. Top of the screen, top right corner is the NFA provided to us. Alongside the transition table of the NFA is listed. Below table is the transition table of the DFA we are constructing from the provided NFA with equivalent power. The transition table of the DFA contains the states in the first column. The states highlighted green and pointed with the star are the accepting states of the DFA. The state highlighted with the inward arrow is the initial state of the DFA, and the states with the cross sign are the states which are not reachable anywhere in the transition table on the transition of input letter A or B. So we can remove those unreachable states in our DFA. First, the state phi state. For phi state, the input letters A and B would lead the transition towards the phi state itself, as the phi state was not present in the provided NFA. So we have the solution that if we don't get any transition in the NFA, then in the corresponding DFA we would point that transition towards the phi state. Next, for the state 1 on input letter A, again we do not have any transition for input letter A in the provided NFA as state 1, so we would be pointing this transition towards the phi state as well. Similarly, at state 1, we have to satisfy the transition for input letter B. As we can see that in the provided NFA there was a transition at state 1 for input letter B from state 1 to state 2. So this would remain the same, as we do not need to take union with any other state. The input letters transitions for state 2 of our DFA. First, we will see the transition of letter A at state 2 in our NFA. In NFA provided to us, there is a transition from state 2 to state 2 and 3 on input letter A. So this transition would remain the same. Now for input letter B at state 2, if we consult the transition table of NFA, there is a transition from state 2 to state 3, which would remain same for DFA as well. Next, for state 3 of our DFA, for input letter A, if we consult the transition table of NFA, we can see that at state 3 for input letter A, there is a transition from state 3 towards state 1. And similarly, on state 1, there is an epsilon transition towards state 3. So we have to concatenate the epsilon or lambda after the input letter. This would result into the transition from state 3 towards state 1 and state 3 on input letter A. Now for letter B, there was no transition at state 3 in the provided NFA. So we have a solution for that, and we would be pointing it towards the phi state or the empty state. Next, for state 1, 2, we have to take a union for the transitions of both of these states separately from the NFA and then display the provided result here in the transition table of DFA. The two states are state 1 and 2. First, we have to take the transition for input letter A on both of these states separately in the NFA provided. On state 1, there is a transition to empty, and on state 2, there is a transition from 2, 3. Union of empty and 2, 3 would result into 2, 3. Now for input letter B at state 1, 2, again we have to consult the transition table of NFA, and for input letter 1, for state 1 on input letter B, there is a transition towards 2, and for state 2, there is a transition towards 3. Again, this would result in 2, 3. We can't ignore the state, but we can ignore the empty state or phi. Next, for state 1, 3, on input letter 1 has a transition towards phi, and 3 has a transition towards 1, and then with lambda concatenation towards 3. So this would result in 1, 3. Now for input letter B at state 1, 3, we will again consult the NFA. For input letter B at state 1, there is a transition towards 2, and at state 3 there is no transition. So this will result in state 2. Next, for state 2, 3, and the input letter is A. Consult NFA. At state 2, there is a transition towards 2, 3. At state 3, there is a transition towards 1. Both of these would united would be united and the result would be state 1, 2 and 3. Next, for input letter B at state 2, 3, we have to consult NFA again. At state 2, on input letter B, there is a transition towards 3. And at state 3, on input letter B, there is no transition. So the result would be the state 3. The last state of our DFA is state 1, 2, 3. Now we have to consult all of these three states in the NFA to satisfy the transitions for both input letters. First, we'll see for state 1, 2, 3 transition arrows for the input letter A. On input of A, 1 leads to 5, 2 leads to 2, 3, and 3 leads to 1. Union of these three would lead us towards 1, 2, and 3. Now for input letter B. State 1 leads to state 2, state 3 leads to state 3, and state 3 leads to 5. The union of 2 and 3 is the 2, 3. Based on the transition table which we have drawn by following the rules to convert NFA to an equivalent DFA, I have constructed the DFA using JFlap. Here in the DFA, we can see that on state 1 there is no inward arrow, which means state 1 is not reachable from anywhere in the DFA. Similarly, for state 1, 2, there is no inward arrow, so state 1, 2 is not reachable from anywhere in the DFA. Therefore, we would remove both of these states from the DFA, and the resultant DFA would comprise of 6 states. That is all. Thank you very much.